Data unknown, a revenue transfer design pattern for revenue protection. How can we forget Donald Rumsfeld? Do you remember his known knowns? Those are questions we do have answers for. His known unknowns? Those are questions we must find the answers to. And of course, his unknown unknowns, questions we don't even know to ask. These are aspects we need to consider when we want to transfer revenue from one source to a destination. How can we be sure that 100% of the data is transferred? Not less, in other words missing data, not more, in other words duplicates, exactly 100%. To do this, we'll need a number of approaches. First of all, we need to ensure that each transaction is uniquely identifiable. So one way to do this is to use a unique transaction number, at least unique over a given period anyway. We need to ensure that duplicate transactions are rejected. So one way to do that is to check the unique identifier and reject duplicates at the destination. And this also allows resending of data without fear of duplicate entries. We need to ensure that transactions are sequential, so that missing transactions can be detected. We should employ a dual entry methodology, whereby a transaction consists of a credit and a debit component in different accounts. We should also use a one-way hash algorithm, which is a good way to detect unauthorized editing of financial data. And then finally, we should use an independent report to verify the completeness across the source and destination databases, using a comparative query. Other considerations include what kind of performance impact will these strategies incur, a very important point normally overlooked. Will there be any contention or locking of data? Also, what kind of data transfer mechanism is going to be employed? XML? Is it going to be file-based or via an enterprise service bus? What's the required frequency of transfers? This affects the financial accuracy at the destination at any given time. What's the expected volume and data sizes of transfers? Sufficient bandwidth must be provided. How will disputed transactions be handled? Reversals? Adjustments? Do different transaction types need to be transferred into different accounts, such as auxiliaries, revenue, tax, etc.? And what kind of service level agreement or SLA is expected? Uptime, redundancy? Finally, what security protocols will be put in place to prevent data manipulation? SSL, robust passwords, auditing? So the first requirement is quite simple. Each transaction should be uniquely identifiable via unique reference in order to identify duplicates and aid in any subsequent identification, and this can be used at the destination to prevent accepting duplicate transactions. But uniqueness, of course, does not guarantee collective completeness to ensure that no transactions are missing. One way to do this is to relate each transaction to its immediate predecessor via a simple sequential count. For example, transaction 2 is related to its predecessor transaction 1, and transaction 1 is related to its predecessor transaction 0. This facilitates sequence checking at the destination. The destination should check that the sequence number is the next one that's expected and alert on any missing data. We also need to consider a sequence rollover. A sequence number cannot increase forever as it will simply get too large. So in practice, all sequential reference numbers must roll over and start again from 0 at some point in time. So the important thing is to ensure that the rollover doesn't happen too frequently, and to ensure, of course, that the source and destination will be able to support the rollover effectively. I'm sure we all remember the story of the princess and the pea from our childhood, where a little pea disturbs the princess's night's sleep even in spite of all the cushions beneath her. Well, funnily enough, the similar thing can happen when updating sequence numbers because it can cause contention. This can happen because multiple sessions are all trying to get the next sequence number from the database. Ultimately, this requires fighting over a particular block in the storage data. Concurrent updates can cause block contention, or what's known as a hot block, and it becomes a serialization point. Databases often provide sequence numbers of their own, but these are memory-based. So if a rollback or a session dies, that sequence number is lost, and of course it won't be sequential then. So then it won't give you the detection for missing financial records. So we need to design a compromise. A number of compromise design strategies can be employed to significantly reduce contention while still ensuring consistent transaction sequences. One method is to use multiple concurrent counters. This isn't sufficient by itself because we still need to avoid the contention at the block level, the hot blocks. So to avoid that contention, the strategy should be combined with storage block sizes which are comparable to the database counter record size. In other words, have one counter record per data block. We also need to consider what happens when we revert to a failover or standby database. There's always some lag time between updates of the primary and standby database, and this could result in potential duplicate transaction sequences if the standby is brought online before all database updates have been propagated. A better design is to allocate counters which are unique to the standby database. We also need to consider data tampering. This can occur prior to the revenue transfer process. Deleting a sequential transaction would of course be detected by the gap in transaction sequence numbers. However, if only the transaction amounts are tampered with, the sequence number order would not detect this problem. To prevent this kind of tampering, use a one-way hash algorithm on the currency amount value and store that with the transaction or for a set of transactions. It's essential to secure the transmission of financial information between source and destination, even when both systems are behind the firewall. The most common way of doing this is with TLS or SSL and public-private keys, the former provided to the sending party. Double entry accounting is based on the fact that every financial transaction has equal and opposite effects in at least two different accounts. It's used to satisfy the equation assets equals liabilities plus equity. This mechanism makes it possible to verify the arithmetical accuracy of the books of accounts by ascertaining whether the two sides of the equation are equal, and then mistakes can be detected. Wherever financial information is managed, a double entry system is recommended. One would also need to look at the revenue allocation process. The revenue transferred will need to be allocated from each source account to the corresponding account at the destination. There are also good guidelines in terms of editing or deleting financial information. It's good accounting practice never to edit or delete that information. Whenever a correction must be made, a double entry adjustment or journal should rather be performed. Auditing should be a key feature of adjustments. An independent report verification is recommended as a final check. Run a concurrent comparison report between source and destination databases for a given period. For example, in Oracle, you can do a minus between two databases. There should be no financial differences. Perhaps it's time to find the unknowns. Thanks for watching.